Welcome to Engineering Innovations, the official podcast of Purdue University's Elmore Family School of Electrical and Computer Engineering, where we explore groundbreaking advancements in engineering with leading experts in the field. I'm your host, Kristin Malavenda, the Communications Director for the school, and today's guest is Dr. Kaushik Roy, the Edward G. Tiedemann Jr. Distinguished Professor of the ECE. Kaushik's research draws inspiration from the human visual system, specifically how our eyes focus on key details while processing the world around us. His work on Foveation-based active learning aims to make AI systems more efficient and able to mimic the way humans concentrate on the most important information. Kaushik, thanks so much for joining me today.
Thank you.
I want to start with the basics, which is, how did you find your way to becoming an engineer?
Yeah, that's always a good question, and I'm not really sure how it all started. Certainly I come from a family where, my father, my uncle, and others actually were in science. My mother wasn't, it was important at that time to be in science so that you can get the right jobs. Growing up in India, I still remember the fact that I actually liked literature, so my parents were a little bit concerned
that you were going to be a liberal arts kid.
That's right, and so this was kind of interesting. But I always liked physics. My father was in physics, in all honesty, he was really one of the best teachers that I had, and it so happened that I ended up being in engineering. I wanted to study physics, but it was at that time. From the jobs perspectives and other things, it was good to be an engineer.
Gotcha. And how did you decide to go into academics as opposed to industry?
That's another interesting, question too. Because when I was graduating, I wasn't sure that I was so much excited about being a faculty, and so I joined Texas Instruments. And I must admit that I learned a lot at TI after my PhD. I went there and I learned a lot. There's quite a few exciting projects that I did. After a few years, a couple of years, I thought that it might actually not be a bad idea to try out academia.
Yeah.
I interviewed at Purdue and a few other places, and I joined Purdue. After coming here, I realized what I missed being in TI. I actually missed my grad student life.
Oh, nice.
And in a lot of ways, interesting ways, actually. In fact, my wife still tells me that I am still a grad student.
I can see that. So you've been researching artificial intelligence for a long time now. How did you get into that area of research, and how has it developed?
Yeah, no, when I graduated, I worked in the area of hardware designs, and then I initially I wasn't working on AI. In fact, I wasn't really sure if that field at that time when I graduated, early 90s, if that field was going to go anywhere, as I started working on circuits and devices, there was a program called NRI, which is a Nano Research Initiative, and I was a part of that program. And we started looking at devices beyond CMOS kind of devices. Mm-hmm. And we started looking at magnetic tunnel junctions and other kinds of magnetic devices. And the interesting part was that those devices were good but could not really replace the CMOS technology. And so we felt that it might actually be interesting to look at some of these devices if they could mimic, and I say quote unquote mimic, I'm using the term very loosely, mimic the neurons and synaptic activities.
Right.
And what we found is that some of these devices were quite interesting and be able to do such mimicking. From then on, looking at some of those neuromimetic devices, we felt that it might be actually interesting to go and see if we can make, AI, deep learning, and all these, implementations of those to be more effective. So I came from, in some ways, bottom up, looking at neuromimetic devices, and then I got later on quite excited about AI algorithms and so on.
When AI first started to be researched, what was the goal, and has that goal changed over the years?
Yeah, I mean, initially, certainly, AI was used, in a lot of these vision problems, and I think it's changing every day.
Yeah.
In a lot of ways, if you think about AI now, it's applicable to each and every area that you can potentially think of.
Right.
So AI is all pervasive. If you're not able to model something effectively, and if you're able to take, and if you have the data available, and if you're able to take a data-driven approach, it turns out AI, in a lot of ways, is applicable anywhere and everywhere.
Nice. So you've kind of advanced onto this foveation-based active learning. Can you explain in simple terms what that means?
Sure. I mean, initial work that we were doing was on, again, vision applications, looking at mainly, object detection, recognition kind of things. But we felt in a lot of ways that the way things were done and the way we were learning was not quite bioplausible.
Okay.
And if you think about it, I mean, certainly we know that brain is quite efficient.
Yes.
And we have an existential proof of that. So the question, of course, was the fact that can we, again, quote unquote, mimic some of those operations of the brain, though we know very little about the brain. So to that effect, we started looking at what we call neuromorphic computing. It's not that standard deep learning is not inspired by the brain. It's certainly weakly inspired by the brain. But then again, going forward, the question was, can we take more cues of whatever little that we know from neuroscience? And in neuroscience, they talk about an active vision system, which is having a dorsal stream and a ventral stream, and the what stream and the where stream in some ways. And what is basically to figure out what that object that I'm looking at possibly is, and the where is in some ways to figure out where that object is going to be. So if you really look at, for example, the eye, in general, when we look at things, we quickly scan the space around us to be able to figure out where the objects are. So we have rapid eye movement, and that's called saccades. And then we are also able to actually sort of focus on a particular area. And that's basically the area, the glimpse area that we have. And we can change sort of the glimpse. The area, there's an area of the eye which is called fovea, which actually helps in that particular glimpse. And we can change the size of the glimpse and all. So, and it turns out that if I am able to learn objects that way, by in a lot of ways ignoring the clutter, the background clutter, we can potentially do not only better learning, but in a lot of ways actually more robust learning.
So what are some of the real world applications? How would your research affect my life?
Again, that's a good question.
Thank you.
Every form of AI that we are doing today, I mean, the researchers are doing today, certainly affects your life. I mean, talking about the field of medication to self-driving cars, you name it, it can affect it. In fact, even I read an article some time ago where talking about AI, being able to paint stuff, which was better than, in fact, even the artist. And in fact, they won the competition, and the human artist got very furious about it. So that basically tells you how well AI has been doing.
Right.
But the kind of things that I'm looking at today are really looking at, for example, as an example, you can take the drone, and if you want to go from point A to point B, what you really have to do is, as quote unquote the humans would do, you would first survey the environment, figure out what things around are, and what's moving, what's not. There's something called optical flow that you figure out. Hey, what are the objects that are moving? What are the objects that are stationary? You do a segmentation of that space, and then figure out, can I track the moving objects in some ways, and then figure out, hey, can I have a path that I can take from point A to point B? So you do that path planning and then take the proper actions of doing this. So if you were to really think about doing all those, it turns out AI can be quite effective in doing, for example, optical flow segmentation, doing, for example, again, at the same time, object tracking. Now, the question, of course, is, hey, can I implement some of those things in the right kind of networks or network architectures? And to that effect, we've been looking at various kinds of network architectures that can be suitable. Not only the standard deep learning, we've been actually also looking at, for example, spike-based computations based on the kind of sensors that we have. If the sensors that I'm going to be just using, for example, is vision sensors going from point A to point B and nothing else, we've been looking at the standard camera that you have here, but also looking at these new cameras that have been developed, which are called the dynamic vision sensors, which gives out spikes as inputs. When there's a relative motion between the object and the camera, you actually produce a spike, else you don't. And if you can effectively use that information to actually come up with better network structures, and in this particular case, we looked at spike-based computation units. It turns out you can actually do better, capture the timing information better, and so on. So fusing these two inputs from the camera, and once you do fuse them together, is it possible that I can actually have a network architecture which is also fused in terms of standard deep learning, maybe combination of these spike-based computation units and so on. So hybrid kind of structures, if you can potentially think of, and doing that can potentially give you efficiency. And better accuracy in what you're trying to do. And so we use that, and then finally at the end of it, that's not the end of the journey. You have to really figure out, hey, how do you implement that in the hardware? And again, from whatever little that we know of the brain, we don't really have a standard von Neumann kind of architecture to do things. We don't have a memory on one side and a compute on the other side. It's all sort of a mixture of compute and memory together. So is it possible that I actually again take some cues from there and try to come up with and compute in memory kind of architecture, and which sort of gets away from what's called the von Neumann bottleneck, meaning thereby that every time I do compute in a von Neumann architecture, I got to get data from the memory, compute, and in the CPU, and then put it back into the memory again, and that's quite inefficient. So is it possible that I do some of these important computations in the memory itself, and to that effect, actually good amount of work that we're doing is trying to come up with a hardware architecture that's going to be quite efficient for some of these computations that we're doing in the network architectures.
Now, in conversations I've had about AI with other faculty members, energy efficiency always comes up. Why is energy efficiency important, and how does your method improve that?
No, I probably should have talked about energy first. That's really, really one of the bottlenecks. And when I graduated from Illinois, my PhD, and then joined TI, one of the things that we started doing there, and then when I came here, I continued that, was on energy efficient low power design. So we were sort of one of the few researchers at that time looking at energy efficiency, power consumption. And now, as you can see, it's like, it's absolutely important. One of the problems that we face today is, the training of some of these huge, large language models that we have, right? Or for that matter, in fact, even the standard AI, the training complexity is large and requires a huge amount of computation efforts. And so energy is really the bottleneck. So the question, of course, is, hey, can I really come up with algorithms and the hardware along with the right kind of sensors? That's going to be quite important too, right? And can I really collect the right data, throw away the not so important stuff, right? And compute in a very, very efficient fashion. So the kind of things that I just mentioned in memory computing can potentially give you, high energy efficiency. The second thing is that some of these network architectures that we're talking about, spike-based computations, and the right kind of sensors along with it, if I, when we said that, hey, when there's a relative motion between the camera and the object as an example,
Yep.
right? If there's no motion, there's no spikes.
Gotcha.
So, hey, you don't do computations.
Yeah.
But can I utilize some of these things, both at the sensor level, the network architecture level, and then going all the way down to the hardware? Can I do co-design of the hardware, the sensors, all the way to the hardware architecture to be able to get the efficiency? Otherwise, I think it's an unsustainable situation.
Gotcha. Now, talking about energy efficiency being a challenge, all of these things that you're working on build upon each other. One is dependent on each other and they're interconnected. What are the biggest challenges you faced along the way in developing better AI systems?
I think it's going all the way from, as I mentioned, it's not just one level of design abstraction, but it's really going, when you're trying to do a system design, you have to really think about going all the way from, sensors to network architectures to the hardware that you're designing. And even at each one of those levels, if you really think about it, the network architecture level, hey, what kind of network architecture is suitable for it? What kind of training methodology should I use? Today we use, for example, standard deep learning, but when it comes to edge devices, is it possible that, hey, can I do some computations which are going to be, or rather training, which is low complexity training? So to that effect, we in our research group and others have been looking also at the possibilities of what we call local training rather than backpropagating. And backpropagation is expensive. Is it possible that I do some local training, which has also been observed in the brain? And with some limited success, we're able to do some of those things. There's a lot more work to be done. But going further down, now at the hardware level, there's a need to really think about, hey, rethinking of that hardware that we had, rethinking of the entire computing stack. So with doing such co-designs, going all the way from the sensors down to the hardware, I think is what is going to be required, and then possibly taking cues from the brain for developing the right kind of training methodologies, the inference methodologies, and so on.
So I know part of being a researcher at the university level is roadblocks. You hit a lot of roadblocks and have to find a way around them or a new way of thinking. When you're working with your grad students, how do you help them learn not to just be frustrated by those, but to use those roadblocks as fuel to find another way?
Yeah, I've been faculty for a while, and I have graduated a few students.
Okay.
And I also have a large group. Today, possibly I have a group of about 35 PhD students. Wow. And they all work in various domains, going all the way from as I said, network architectures, learning algorithms to the hardware level, and looking at also some of these neuromimetic devices that can potentially alleviate some of these energy efficiency problems. There will be roadblocks. I told them all the time. When you join, in our group as a PhD student, the first thing I say is that this is going to be quite different from bachelor's or master's. We need to work together. We're going to work on problems that you don't know and I don't know.
Right.
If we know it, then we're not going to work on it. So, this is a journey.
Right.
You got to enjoy it. And there will be times that you're going to be very, very excited when you get the results, and there'll be times when it's not going to be exciting. We're not getting results. We need to find new ways, think about new kinds of methodologies to be able to solve these problems. So it's a journey.
Yeah.
There'll be ups and downs, but we really look for those exciting times when you get the results, when we, the ecstasy, so to say. Yeah. And then it's a journey, and you got to enjoy it.
Right.
Yeah? And we need to work together. We need to have fun in the work together. And once you do that, things in some ways happens magically.
Yeah.
People ask me the question, how do I come up with a problem? Early days when when I was a professor and the student comes, I had a harder time telling them in some ways that it takes a little time doing that. But these days I said, hey, people have graduated from our group, a lot of these guys, there are certain formula that we do look at. I mean, certainly you have to put effort, look at, read papers, understand the area, and, get your hands dirty doing some, maybe the known things.
Right.
And then the magic happens.
So when you're
and
looking,
it is really magic.
Yeah, I can imagine. When you are looking for students to join your research group, what qualities do you look for in that student that make you think, okay, this is going to be a good addition to the group?
That's always you go with your gut.
Okay.
Certainly, some students are quite good in taking exams, and some students are really good in thinking. So when you talk to them, you get the feel of it, right? So it's not always getting an A in the course,
Right.
But what is really important is to be able to, think and be open about things, and that is something which is really important. And at the end of it, once you get started, there's no substitute for hard work.
Right.
So I usually tell them, if you have the inclination, I have the time.
Gotcha. When you're doing research, I know over the years, interdisciplinary research has become more and more important. How does that figure into what you're doing, and what are the areas that you're most likely to collaborate with on your research?
Yeah, I mean, this is AI, certainly is very, very interdisciplinary. And so if I were to really think about the hardware design part of it that I was talking about earlier, that's very large-scale integrated circuit designs, could be devices, the MN area, the VLSI area. Those are quite important, and we've been doing work in both the areas. On the other side of it, if you really think about the algorithm part of things, that can certainly go in computer engineering, right? But more importantly, can also go in computer science, right? And the algorithm designs and all. And there's a good number of people working in that area. Some of these can go into statistics and other areas, math, statistics and all. So it is very, very interdisciplinary. We also need to know signal processing, because initially a lot of things are image processing that people have been looking at for vision problems, as an example.
Right.
Image processing techniques were being used. And, the reason why these are all important is that, hey, can I take, combination of some of these techniques from different areas, and then, add data with it to be able to do actually, much better inference, and at the same time, maybe also at the same time, be able to do, more efficient training, more efficient, hardware implementations. So I think it's a very, very multidisciplinary area. And then if you bring in applications, the medical area, you name it.
Yeah.
It's agriculture, it's just there.
Yeah. I think it's amazing that I've learned since being the communications director here that engineering touches everything that you do. And with electrical engineering, if there's something electric involved in it, you've got to have an engineer. And I think people maybe have a misconception about engineering and what exactly it is. What would you tell people, what makes engineering exciting?
I mean, it's a multidisciplinary nature, and you can potentially work in, different areas. And I forgot to mention neuroscience. Right?
Oh, right.
And, as an example, you can have, you might be working in neuroscience and then really thinking about, hey, if I can do some of these implementations in hardware, or for that matter, algorithms, maybe I can learn more.
Right.
On both sides of the aisle, one the neuroscience side of things, and the other is basically the AI side of things, and we can learn from each other.
Yeah.
That's one example of it. But then again, if you are, for example, in mechanical engineering, I'm just going to give you another example of it, that all the chips that we are designing now, when it comes to energy efficiency,
Right.
talking about power consumption, cooling becomes an important issue, right?
Yeah.
And if you really want to look at some of these cooling technologies and all, I mean, a lot of these are being developed in mechanical engineering.
Gotcha.
Right?
Yeah.
As you can see today, the Nobel Prize in Physics was given to, in some ways, AI.
Yeah.
The Nobel Prize in Chemistry this time was given, in some ways, to AI.
Yeah. I think you're right that it's everywhere, right?
It's-
and I don't know that people completely understand it, but you hear about it all the time. So like over the next, I don't know, 10, 20 years, what do you want to achieve? If you could, what's your end goal in your research? And do you ever see yourself, I feel like professors don't ever really retire. You have a retirement party and then they're back in their office the next day. So as your career advances, what would you like to do?
No, retirement doesn't come to my mind. What do you retire from?
Yeah, right.
And what do you end up doing? And so, it's a fun area. Really having fun. The goal is to carry on having fun and to solve some interesting problems. So I don't know.
Yeah.
My goal is to have fun. Keep having fun.
And just learn what you don't know.
And keep learning what you don't know exactly. And the learning part of it is absolutely important. And sometimes I say that, as a part of this learning process, we do research.
Yeah. So when you're not researching or teaching, and it's an interesting question to ask what you like to do in your free time, because I feel like all the faculty I've interviewed so far like doing their research, and that is fun for them. But when you're not doing that, what kind of things do you do to relax and just kind of recharge?
Yeah, I talked about literature.
Mm-hmm.
I still love it.
Yeah.
And I still read a lot of books.
What kind of books do you read? Like where?
The latest that I'm reading is by a writer from Tanzania, Abdulrazak Gurna.
Okay.
But I've been reading a lot of books on different areas, and my wife sometimes complains that I only read Nobel laureates in literature.
Yeah, you're reading literature.
Yeah, and to that I say that I don't have the time to vet stuff. Somebody has vetted it for me.
Right.
So,
It's a good point.
Yeah, but yeah, it's been that's something that I really enjoy. And the other one is I like playing tennis. I like playing badminton. In fact, yesterday I was actually playing badminton with my students.
Oh, wow.
So we do every week end up going and playing badminton. I like doing exercise,
Yeah.
running. I've stopped running a little bit now because that can give you a little bit of a knee problem. But
Right.
I do keep myself active. Still go out and play.
Do you
badminton
have-
these days.
Do you
with
have
my students.
kids?
I do.
And
I do.
you mentioned how maybe your family makeup influenced your decision to go into engineering. Do you see that in your children, that bent to go towards engineering or problem solving?
Again, I don't want to sort of in some ways, tell them
Right.
what they should do.
Yeah.
But we have to create the right kind of background for them and right kind of environment for them.
Mm-hmm.
And the environment certainly is science in a lot of ways.
Yeah.
I mean, either intentionally or otherwise. So I have a son
Yeah.
who is in the 11th grade.
Okay.
So soon he'll be thinking about going to college and
Right.
what to study. I think he's interested in science. He told me the other day, I was just chatting with him what he likes. He said math.
Nice.
I also have my nephew, who came to Purdue to do
Okay.
his PhD. He ended up choosing electrical engineering.
Good choice.
Yeah, it's a good choice. That's his choice,
Right.
I hope. Yeah, so yes, we'll see how things go. But
What does your wife do? Is she a STEM person?
no, she's not.
Okay.
She was in marketing and communication. She used to be
Oh.
the director of marketing and communication for Purdue at one time.
Oh, okay.
Yeah, earlier.
That's
But,
also a good choice. But
yeah,
not
that's
that
an
I'm
interesting
biased,
choice. Yes.
well, thank you so much.
And I like journalism too.
Yeah.
And as I said earlier, that I used to come to work and I used to hear your name in NPR News.
Back when I
that
was on
good. Yes,
WBAA.
absolutely.
Yeah, that was a fun
Yeah.
a fun time. So, well, thank you so much for joining me today and shedding some more light on artificial intelligence.
Oh, thank you. Enjoyed it.
So that brings us to the end of today's episode of Engineering Innovations. It's the official podcast of the Elmore Family School of Electrical and Computer Engineering here at Purdue University. If you found today's conversation as interesting as I did, don't forget to subscribe, leave a review, and share this episode with anyone who's curious about the future of AI. We'll continue to bring you the latest innovations and discussions with thought leaders shaping tomorrow's technology. And for more information on Purdue ECE and all the places you can find us on social media, you can check the show notes. We'll have links there. And if you have suggestions of topics for future episodes, please feel free to comment on our social media posts and let us know. Until next time, I'm your host, Kristin Malavenda, and we'll be back next month with another new episode.